Welcome to the deep dive. We cut through the noise to bring you the core insights from some really complex topics.
I'd be here.
Today, we're plunging into the mind of Ludwig Boltzmann. He was this Austrian physicist, and his ideas about atoms and heat, well, they basically laid the groundwork for how we understand reality statistically.
Absolutely. He was truly revolutionary, way ahead of his time, really, and faced a lot of skepticism.
Yeah, long before people were really ready for it.
That's right. His insights, they didn't just contribute to physics, they pretty much sculpted the landscape for what came next. And if you ever see a picture of his tombstone,
Oh, yeah.
you'll see his most famous equation right there, SKLNW. It's like more than just math. It's a statement about existence itself.
And that's really our mission for this deep dive, isn't it? We want to unpack that equation, explore Boltzmann's foundational work, and then connect it to a more modern idea, this thing called motion theory.
Which is this perspective suggesting Boltzmann was, maybe without fully realizing it, describing a universe where motion is, well, everything.
Yeah. The only thing there is, right? So the goal here is to give you, our listener, a kind of shortcut. You get to be well-informed on this pretty deep subject, maybe see some surprising connections.
And hopefully have a few of those aha moments.
Exactly. So let's dive in.
Okay, so to really get Boltzmann, you have to picture his time, late 19th century.
Right.
A lot of scientists, maybe most, still thought heat was some kind of invisible liquid. They called it caloric.
Caloric, like it flowed between things.
Yeah, exactly, from hot to cold. And the whole idea of atoms, these tiny things constantly moving, that was still pretty controversial, met with a lot of resistance.
It's kind of wild to think about that now.
It is. But Boltzmann, he wasn't just guessing. He built the mathematical framework for a totally new way of seeing things. He argued, pretty boldly, that heat isn't some weird fluid. It's just, well, the collective motion of countless particles.
Just motion.
Yeah.
Simple as that, fundamentally.
Fundamentally, yes. And that famous equation, SKLNW, that became the cornerstone of statistical mechanics. It's how we quantify disorder or randomness.
Okay, break that down for us. SKLNW.
Right. So S is entropy. That's your measure of disorder.
Got it.
K is Boltzmann's constant. Think of it as like a conversion factor. It connects the tiny world of atoms to the big world we see.
The micro to the macro. Okay.
And W, that's the key part. It's the number of ways the tiny parts of a system, the particles, their positions, their speeds can be arranged without changing the overall state we observe, like the temperature or pressure.
So like for gas in a box, W is all the different ways the molecules could be bouncing around, but the gas still looks the same to us.
Precisely. The more ways those particles can be configured, the higher W is, the higher the entropy.
So disorder isn't just stuff being messy. It's about probability, the number of possibilities.
Exactly. It's the probability of arrangement. Boltzmann basically gave us the math to describe the inherent freedom or wiggle room motion has within any system.
He was writing the math for motion variety, even if he didn't call it that.
You could say that, yeah. Giving us the tools to see the sort of statistical fingerprints of reality's dance.
That's a great way to put it. Okay, so let's jump forward. Boltzmann lays this incredible foundation. Now, what happens when we look at his work through this newer lens, motion theory?
Right, this idea that motion is the only thing there is.
Which is a pretty huge claim. How does it change how we see Boltzmann's work?
Well, it doesn't throw Boltzmann out, not at all. It actually sees his work as like the essential skeleton. It builds on it, deepens it.
Okay, give us an example.
Let's take heat again. Boltzmann correctly said it's collective particle motion. Motion theory refines that. It says heat is the unsynchronized component of structured motion at a given scale.
Okay, unsynchronized component of structured motion. That sounds dense. Can you unpack that a bit?
Sure. Think about something really ordered, like a perfect crystal lattice. Every atom is sort of vibrating in place, but in a very coordinated way. Highly synchronized loops of motion. That creates structure.
Like a perfectly timed dance routine.
Exactly. Now imagine those little loops of motion start getting messy. They lose their perfect timing, they jostle each other, become more random, more chaotic. That uncoordinated part, that jumble, that's what we feel and measure as heat.
Ah, okay. So temperature is just measuring how chaotic that underlying dance is.
Got it. It's a reading of how chaotically the motion loops are behaving.
Okay. The dance routine turning into a mosh pit. I can picture that.
It's a decent analogy, yeah.
So if heat is this chaotic, unsynchronized motion, how does motion theory look at entropy? Boltzmann said it was probability, the number of ways, W.
Motion theory sees entropy as the statistical measure of how far a system's structured motion has drifted from tight synchronization.
Drifted from sync.
Okay, so when Boltzmann talks about W, the microstates, motion theory says those microstates are just different possible patterns or configurations of these fundamental motion loops.
So low entropy means high sync density. The loops are tightly coordinated, locked in step.
Exactly. Fewer ways for them to be arranged without changing the overall structure. Like that marching band you mentioned, imperfect formation, very constrained.
And high entropy.
That's low sync density. The loops are much freer, more chaotic. There are many, many more ways they can be arranged, more possible configurations.
And that's why things tend towards higher entropy, because there are just more ways to be messy and out of sync.
That's the statistical tendency, yes. Motion naturally drifts towards less tight alignment, less synchronization, unless you actively pump energy in to reorder it, to force it back into sync.
Which brings us to gases. Boltzmann refined the kinetic theory, right? Particles moving, hitting walls, causing pressure, temperature linked to their energy.
Yes, foundational stuff. Gases are particles in constant random motion. Pressure is collisions with the container. Temperature relates to the average kinetic energy.
How does motion theory build on that?
Instead of just particles, it talks about tiny structured motion loops. Each gas particle is one of these loops. And a collision. It's not just a simple bounce, it's a sync interruption.
Well, sync interruption.
Yeah, where these loops interact, briefly exchange motion, and maybe realign their patterns or phases.
So the pressure on the walls of a container isn't just tiny balls hitting it. It's the combined effect of countless microsync disruptions per second.
That's the idea. The gas itself isn't just particles in space. It's seen as a statistical cloud of motion loops, constantly rephasing through interaction.
It shifts the focus from things moving to the movement pattern itself.
Exactly. It's about the dynamics of the motion, the patterns of interaction, and Boltzmann's math gave us the first real way to handle these statistics.
Now, Boltzmann didn't just stop at gases. He thought big, like cosmos big.
He did. He applied statistical thinking to the universe itself. There's the idea of Poincaré recurrence, that in an infinite system, any state will eventually repeat.
Which sounds pretty mind-bending.
It is. And he even speculated that maybe our relatively ordered low-entropy universe is just a rare temporary fluctuation in a much larger, mostly high-entropy disordered cosmos.
Kind of suggests everything is slowly winding down towards a heat death, doesn't it?
That's the traditional thermodynamic view, yeah. A bit bleak, maybe.
But motion theory offers a different picture.
A much more dynamic one, I think. It suggests the universe isn't just passively drifting towards maximum entropy, towards heat death. It sees it as a motion cascade.
A motion cascade. What does that mean?
It means sync density. The level of ordered, structured motion isn't just lost forever. It builds up in some places, dissolves in others, in ongoing cycles.
So reality isn't just decaying, it's constantly rearranging.
Exactly. Rearranging motion into new sync structures. Think about star formation, galaxy clusters. Those are zones of incredibly high sync density emerging from less structured states.
Or life itself.
Life is a prime example. Highly ordered, localized sync structures that maintain themselves by pulling in energy and motion from their surroundings, temporarily bucking the overall trend towards disorder. Even consciousness
could be seen as a complex sync network in the brain.
That's the interpretation, yes. A self-maintaining pattern of synchronized motion loops. So entropy, in this view, isn't the end of the story.
It's more like a redistribution step, allowing new patterns to form.
Precisely. A redistribution step in the larger motion story. It allows the universe to reshuffle the deck, enabling new kinds of structure and complexity to emerge. It's fundamentally cyclical, not just a one-way street to decay.
That makes Boltzmann's work even more crucial then. He gave us the math to describe these rearrangements, these statistics of structure.
Absolutely. That's why motion theory considers his work the statistical skeleton. He quantified how many ways motion can arrange itself.
Right.
He showed that the stability we see, the macroscopic world, emerges from this underlying microscopic chaos, this constant motion.
Improved heat and temperature are just different ways of looking at that motion's behavior.
Yes. And his constant K is just beautiful. It's the bridge, the scale converter between the micro and macro motion worlds.
And motion theory actually translates his equation, SKLNW.
It does. It rephrases it as something like sync drift, scale constant, log of possible motion configurations.
Sync drift, meaning the loss of that tight synchronization.
Exactly. Loss of tight loop alignment. So whenever entropy changes, goes up or down, what's really happening fundamentally is the underlying motion loops are finding more or fewer possible ways to dance together, more or fewer rhythms available to them.
It all comes back to the patterns of motion.
It does.
It sounds elegant now.
Yeah.
But as you said, Boltzmann faced a tough crowd.
Oh, absolutely. A huge uphill battle. Remember, caloric theory was dominant, atoms were suspect. His whole statistical approach, it felt alien to physicists used to strict deterministic laws.
Cause and effect, not probabilities.
Right. He was pushing for this microscopic realism, this idea that reality is made of discrete interacting systems, motion systems in the new view. He got a lot of pushback, even ridicule.
Which makes his perseverance even more remarkable.
Totally. And that's why motion theory honors him. He stood for that microscopic realism. He quantified the freedom of motion. He gave us the mathematical language to talk about order, chaos, and how systems transition between them.
He basically built the foundations needed to understand the universe as this dynamic, evolving dance.
Couldn't have said it better. And when you take that foundation and view it through the motion theory lens, the implications spread everywhere.
Like galaxy formation.
You can see galaxies as high sync density zones condensing within these huge gravitational motion fields.
And life again?
Life emerges as these incredibly complex, localized sync structures. They fight entropy, sure, but they do it by importing and structuring motion from outside. They're like little eddies of order in the flow.
In consciousness.
A self-maintaining, high sync density loop network. The brain constantly working to keep its complex patterns of motion going.
So at every level, from atoms to galaxies to us.
Entropy is kind of like the slack in the motion fabric. It's the measure of the room available for rearrangement, for repatterning, the potential for change.
So wrapping this up, Boltzmann showed us that what looks like randomness, like chaos, is often just, well, motion taking the scenic route, as the source put it.
Yeah, he gave us the math to count the ways, the combinatorics of reality, all the possible arrangements.
Even if he didn't frame it as all being permutations of just one fundamental thing.
Yeah,
motion.
Exactly. Boltzmann counted how motion can be arranged. Motion theory tries to explain why motion is the fundamental constituent and how these arrangements arise and cycle.
It's a fascinating progression of ideas. Now, for you, our listener, here's something to chew on. How does thinking about the world this way, as fundamentally motion in different patterns, change how you see things?
Yeah, what other things that seem solid or static or just complex could actually be understood differently, maybe as just part of this universal possibility space of motion?
Different permutations constantly shifting and repatterning. It's definitely something to think about. We hope this deep dive gave you some new perspectives.